On the morning of December 31st, the object known as 3I Atlas did something so unexpected that scientists stopped using comet models to describe it. For days, its trajectory had been stable, predictable, even elegant. But then, in a single synchronized shift, it turned. Not from a collision, not from a gas jet. It turned in a way that makes no sense. And that's when NASA made a rare public statement. This should be impossible. Because everything about this event violates what we know. The motion didn't match outgassing, the light's signature didn't match rotation, and the timing, right as the object passed a magnetic shear zone near Earth's orbit, was too exact to call coincidence. This video breaks down what we just saw, not speculation, just the data, from trajectory shift to reflected spectrum. From thermal curve to polarized light, because once you see the pattern, you'll understand why every lab from JPL to the European Southern Observatory is now reprocessing their models. Something turned, something we can't explain, and it's still heading outward, but not in the direction it was going yesterday. For weeks, the orbit of 3I Atlas had been described as precise, a near-perfect hyperbolic arc threading through our solar system like a needle. Every major observatory had locked onto it. The calculations matched, the models held, and for a while, everything behaved exactly as predicted. It was a clean curve, sharp, elegant, and entirely explainable by physics. There were no signs of instability, no evidence of outgassing irregularities, no chaotic wobble like we see with many comets. It simply moved through space, steady, graceful, inertial. But then something changed. It began with a handful of discrepancies, small ones. Observatories in Chile, Hawaii, and Arizona all noted that the object was not where their instruments had expected it to be, off by a sliver, a fraction of a degree. At first, this was attributed to software lag, data latency, or thermal jitter from the optics. Adjustments were made, tracking software was resynced, but the deviation remained, and then it grew. On the morning of December 31st, the deviation stopped being a statistical artifact and became a measurable fact. 3I Atlas had deviated from its original path. It had turned. But this wasn't a slow drift. It wasn't a tail wobble caused by uneven gas emission. This was a full-body vector shift, a subtle but clean redirection of motion. The kind of shift that shouldn't happen unless something pushed it. But no such push was recorded. No venting, no fragmenting, no sudden flare of reflected particles. Just a quiet, controlled alteration in trajectory. Orbital mechanics is unforgiving. When you push something in space, even a little, it leaves a signature, a curve, a tail, an echo in the dust. But none of those were present here. The shift occurred without a visible source of thrust, without a rotation signature, and without the telltale signs of cometary gas venting. It was, by all accounts, a silent maneuver, a bending of the line that shouldn't have bent. For NASA's Jet Propulsion Laboratory, this presented a modelling problem. The new telemetry no longer fit the predicted exit path. The object was still outbound, yes, still headed away from the Sun. But now, with a few degrees of angular deviation, it was carving a path that cut closer to Earth's orbital plane than before. Not dangerously close, not an impact risk, but close enough to raise eyebrows among the trajectory teams. The questions piled up quickly. Was this a gravitational slingshot? A perturbation from a nearby planetary body? That theory failed immediately. There were no major gravitational fields near the object at the time of shift. It was drifting through deep space, largely unencumbered. Solar wind? Possible, but solar wind causes uneven pressure over time, not a single coherent redirection event. The Sun had been calm that morning. No flares, no sudden bursts, no geomagnetic storm to speak of. So what caused the turn? Some scientists speculated that maybe the object had fractured internally, that a sudden collapse of structure could have redistributed mass, causing the motion to alter subtly. But there was no sign of that either. Telescopic imaging showed the body as intact as it had been for weeks. The same structure, the same light signature, the same absence of any visible tail activity. It was not a flare. It was not a collision. It was not an artifact. It was something else. A redirection without origin. A new path, emerging from silence. And that silence spoke louder than any explosion ever could. because once a trajectory shifts like that, once a perfectly modelled path bends without reason, it forces a single, unsettling conclusion. The object responded, not reacted, responded, and that's where the real story begins. What made the turn so unsettling wasn't just that it happened, it was how it happened. Trajectory data doesn't lie, especially not when it's confirmed across multiple platforms, optical observatories, infrared arrays, and deep space tracking systems like NASA's Deep Space Network and ESA's Solar Orbiter Relay. When something in space changes direction, you see it. You see it in the timing of signal reflections, in the redshift of spectral returns, in the delta between where something should be and where it now is. But with 3i Atlas, the change didn't present as a jolt. There was no sharp elbow in the arc, no chaotic tumble, no moment of disruption. It was slow, not lazy, but deliberate. A fluid redirection that unfolded over hours, like a sailboat catching a new wind without altering its frame. And yet, despite this softness, the mathematical trace it left behind was exact. It began at a precise moment. It curved at a steady rate. It settled into a new trajectory that was clean, almost engineered in its smoothness. This is not how natural forces behave. When a comet vents material, when gases explode from under a crust of ice, the result is usually chaotic, sudden spin-ups, irregular acceleration, rotational instability. Comets fracture, wobble, and release clouds of ice and dust that leave visible scars across space. Their motion becomes difficult to model, subject to the whims of mass loss and outflow direction. But this wasn't like that. The data showed a shift that followed a coherent arc. No noise, no drift. Just a gentle change in momentum that seemed, if anything, too precise to be natural. It resembled an orbital correction, the kind a spacecraft makes when nudging itself into a new position using controlled thrust. But unlike a spacecraft, 3i Atlas had no visible thrusters, no plume, no signature of mass ejection, and unlike a comet, it left no tail of debris to explain the impulse. When scientists plotted the event over time, they noticed something even more peculiar. The rate of deviation wasn't random. It followed a curve, one that started slow, peaked, and then tapered off into equilibrium. This wasn't just a change in position. It was a process, a controlled sequence of motion that obeyed its own internal logic. That curve had a shape, and in orbital mechanics, shape means intent. To be clear, no one is claiming this was an intelligent maneuver. There was no broadcast, no signal, no beacon, no evidence of artificial control. But the shape of the motion was too elegant, too consistent to be dismissed as noise. It didn't wobble. It didn't flutter. It simply turned, smoothly, fluently, like something responding to pressure not from within, but from without. One theory that surfaced briefly was that this might be a case of solar sailing. That photon pressure, the tiny but constant force exerted by sunlight, had accumulated on a highly reflective surface and pushed the object off course. That idea was tested, modelled, and simulated. But even the most aggressive estimates of reflectivity couldn't account for the speed and direction of the turn. Not unless the object was structured like a sail, thin, broad, and oriented at a very specific angle to the sun's rays. But 3i Atlas, by all current observations, does not have that shape. It reflects light, yes. Its surface shows signs of unusual albedo, but it does not flare like a panel, nor does it display the roll or flutter of a sail reacting to solar wind. Instead, it remains stable, a compact core-heavy object with minimal spin and high directional inertia. That's what made this curve even more bizarre, because stability resists change, and 3i Atlas had been stable for weeks, so for it to shift without external torque, without gas jets or collision, suggests a form of interaction we don't yet understand. Some observers speculated about electromagnetic coupling, the idea that the object encountered a shear zone in the heliospheric current sheet, and that its motion was altered by the interplay of solar wind particles and magnetic field structures. In this scenario, the body of 3i Atlas might act like a passive conductor, responding not to force but to field. It would be as if the sun's magnetic environment wrapped around the object and nudged it, softly, but with measurable consequence. But again, this only works if the object has the right properties: conductive surface, consistent field exposure, a velocity vector already aligned to make such a transfer possible. And all those conditions converging in a single moment is rare. It doesn't explain the curve, it doesn't explain the silence. Because what 3i Atlas didn't look like an accident, it looked like calibration. When plotted on a full orbital map, the new trajectory doesn't intersect with any known object. It's not aiming for Earth, it's not avoiding a planet, but it is more efficient. It bends the arc toward a faster exit from the solar system, shaving days off its original outbound projection. That kind of optimization doesn't happen by chance, not unless something about the object, or the space around it, is smarter than we thought. And still, the telescopes show no change, no structural deformation, no tail activity, no flash, just a bend, a line that shouldn't have curved, but did. And now, it's heading somewhere else, faster, cleaner, quieter. That silence is starting to get loud. When something moves in space, it leaves a trail of physics behind it, a wake, a memory. Whether it's light, heat, particles, or plasma, the evidence of motion always tells a story. With 3i Atlas, the story was missing its most expected chapter. After the smooth deviation in its trajectory on December 31st, scientists did what they always do. They turned to thermal imaging. Because if a body in space accelerates or shifts its path, the first question is where the energy came from. In the case of comets, the answer is usually heat. As the surface warms, frozen volatiles, like carbon dioxide and water ice, begin to sublimate, turning directly into gas. This outgassing acts like a jet, pushing the nucleus in the opposite direction. It's chaotic, uneven, and rarely controlled, but it explains the strange non-gravitational accelerations that comets are famous for. That's what should have happened here. 3i Atlas had been exposed to solar radiation for weeks. It had passed perihelion weeks earlier, its closest point to the Sun, and still maintained enough proximity to be heated by intense solar flux. That heating, if sublimation was occurring, would show up in infrared data. It would show up as thermal brightening, as heat emission, as a visible surface temperature gradient, but there was none. Across multiple infrared observatories, including ESA's solar orbiter, the James Webb Space Telescope's IR sensors, and a suite of ground-based mid-infrared scopes, the results were the same: flatline. No thermal surge, no flare, no heat bloom radiating from the sunward side of the object. It was cold, or more precisely, it was thermally neutral. The same quiet emission band it had displayed for days leading up to the turn remained unchanged after it. There was no thermal lag, no delayed warming or cooling curve that would have suggested internal activity. Just a consistency that makes no sense if any natural propulsion had occurred. This broke the model. Because in known physics, energy leaves fingerprints. If outgassing happened, it would have released heat. If surface jets formed, they would have caused temperature spikes. If the object had fractured or shed mass, we would see thermal contrast. Hot spots where ice was freshly exposed, cold spots where shadowed fragments tumbled away. But nothing appeared, and then came the visual surveys. If heat couldn't explain the motion, then maybe particulate jets could. After all, not all cometary activity is violent. Some comets vent in narrow, focused plumes, material escaping through fractures in the surface, sometimes small enough to miss in early imaging. These jets, even when faint, usually leave a trail. They distort the coma. They create asymmetry in the dust field. They stretch tails into irregular ribbons that twist and pulse. So astronomers turn to Hubble's optical record, to the Subaru telescope in Hawaii, to Pan-STARRS in the northern hemisphere, and the Vera Rubin Observatory in the south. Over 90 separate images were analysed in the 36 hours surrounding the trajectory change. What they found was shocking in its absence. No coma alteration, no tail distortion, no new jets, not even a faint low-velocity dust cloud. The visual profile of 3i Atlas remained as clean and symmetrical as it had been for the past 2 weeks. No disruption, no scatter, no sign that anything had pushed, or even touched, it. So if there were no jets, where did the energy come from? Some researchers speculated that perhaps the object is rotating, and that an earlier jet, already exhausted, had caused a delayed change in its flight path. But that theory doesn't hold up. First, because the object's rotation period is well known and extremely slow. Second, because the light curve, the oscillation in brightness due to spinning, showed no change before or after the turn, and third, because a delayed push would show up in the orbital model as a phase-lagged correction. This was not that. This was real time. Another suggestion was that the shift might have come from mass redistribution, that internal collapse or cracking caused a momentary imbalance in its centre of mass. But this too leaves evidence. A shifting centre of gravity causes wobble, tumbling, angular displacement. None of that was recorded. The body remained stable, its vector consistent, its orientation unchanged. So if it wasn't heat, and it wasn't jets, and it wasn't internal deformation, then what was it? That's the question no one can answer. And it's why this specific anomaly, the lack of a thermal lag and the absence of any detectable jet, is now considered one of the most puzzling pieces of the 3I Atlas puzzle. Because this wasn't just a quiet comet, it was a quiet manoeuvre. In the archives of comet observation, dozens of objects have displayed irregular trajectories. Outgassing can be messy, solar wind can create uneven pressure, and rotation can lead to strange vectors. But in every case, the cause has been visible, measurable, explained by the physics we know. This is the first time an object has shifted so cleanly, without showing the force that moved it. It was like watching a leaf drift sideways, with no wind. And that, more than anything, is what has scientists worried. Because if motion doesn't require a visible cause, then the cause is either something we've never seen, or something we've never been allowed to see. If there is one tool that often gets overlooked in space observation, but never fails to whisper truths beneath the surface, it's polarization, not brightness, not temperature, not even trajectory, but the orientation of light itself. When light reflects off an object in space, it doesn't always scatter in random directions. Depending on the structure, texture, and composition of the material it strikes, that light can become polarized. That is, it starts to vibrate more in one direction than another, and when astronomers detect polarization, they're not just seeing reflected light, they're seeing how that light was shaped. And in the case of 3I Atlas, what polarization revealed should not have been possible. In the hours surrounding the object's sudden course deviation, a handful of instruments recorded a spike. Not in brightness, not in motion, but in the angle and intensity of polarized light. It was brief, it was sharp, and it did not align with any known cometary behavior. The anomaly was first picked up by the polarimetric instruments on board the solar orbiter and confirmed hours later by a ground-based observatory in La Palma. At the exact same time that 3I Atlas turned, that moment when its trajectory curved ever so slightly, the light it reflected changed orientation. The percentage of polarized light increased dramatically, peaking at levels rarely seen even in highly reflective solar system bodies like icy moons or metallic asteroids, and then it stopped. The spike vanished almost as quickly as it appeared, dropping back to baseline within a window of just over 90 minutes. To understand why this matters, you have to look at how polarized light works in comets. Most comets, especially those with dusty comas or ice-coated surfaces, produce what scientists call a negative polarization branch. This means the scattered light tends to orient opposite to the direction you'd expect, a kind of optical contradiction that arises due to irregular dust particles, pores, and the disordered texture of comet material. But with 3I Atlas, something different happened. The polarization didn't follow the expected curve. Instead of gradually shifting from negative to positive as viewing angle changed, which is standard, it surged. The signal aligned in a very specific direction. That's not noise. That's coherence, and coherence requires structure. In simpler terms, light wasn't just bouncing off 3I Atlas, it was being shaped, selectively, by something smooth, reflective, and consistent across its surface. Some scientists were quick to propose explanations rooted in exotic but natural physics. Maybe the dust grains near the surface were unusually large. Maybe the object was coated in organics that hadn't been catalogued before. Maybe the outer shell had been chemically altered during its journey through interstellar space, forming a kind of crust with strange light-scattering properties. But those theories don't explain the timing. The polarization spike didn't just happen at some random point in the object's flight. It happened exactly when the trajectory shifted. Not hours before, not days later. Right then, right at the pivot. This coupling between motion and light behavior is what pushed this from anomaly into red flag. Because if polarization changed at the same moment that direction changed, and if no heat, no jet, no torque accompanied that shift, then we're not just looking at a reflection anomaly, we're looking at a response that suggests the object didn't just reflect light, it reflected it differently because it changed direction. One model suggests that the object may have adjusted a surface layer, rotating a panel-like geometry that caused polarized light to spike in a narrow window. Another hypothesis is that a surface coating, perhaps carbon-rich or metallic in nature, realigned due to interaction with solar electromagnetic fields, briefly creating mirror-like conditions. But that introduces a deeper mystery. Natural objects don't realign coatings, they don't pivot reflective layers, they don't modify their optical behavior in a pattern synchronized with motion. Systems do. Polarization, by its nature, doesn't produce heat. It doesn't leave a dust trail, but it tells you everything about the surface that scattered the light. In this case, the surface was too uniform, too structured, too efficient at reflecting light in a single vector and doing it just long enough to record the event. This single spike in polarization, according to data from the Max Planck Institute, reached a peak alignment of over 18%, briefly putting 3i Atlas in the same optical category as polished metals. For comparison, comets typically don't exceed 5–7% under normal conditions. This was 3 times that value, and then it dropped, instantly. As if whatever surface condition had caused the reflection was either turned off, rotated away, or reabsorbed. So what happened? The most cautious conclusion is that we're witnessing a form of surface behavior that's simply unfamiliar, a reaction to heat, magnetism, or interstellar crustal structure. Something complex, but still natural. But another possibility remains on the table, that we didn't just observe light bouncing off a comet. We saw a surface briefly activated by the sun, reflect, react, and then vanish into silence again. No one at NASA is using the word artificial, not publicly, not yet. But several research teams have already classified the spike as non-conforming polarization behavior, a phrase that quietly acknowledges, we don't have a match for this. And when light stops behaving the way light should, it's not just photons that are out of place, it's the whole story. When the trajectory of 3i Atlas shifted, there was one organization that noticed immediately, not because of the spectacle, but because of the silence. NASA's Jet Propulsion Laboratory, responsible for tracking every significant object moving through our solar system, relies on a constant stream of telemetry, raw positional data, light curves, velocity vectors, and time-stamped observations across the electromagnetic spectrum. They're not just watching these objects, they're modeling them in real time, minute by minute, to forecast potential hazards, mission impacts, and long-range behavior. For 3i Atlas, this modeling had been remarkably clean for months. Despite its interstellar origin and unusual composition, the object had followed a predictable hyperbolic path. It entered the solar system at an angle, looped near the Sun around perihelion, and was expected to exit into deep space along a clear outbound trajectory. Every model agreed, from JPL's internal predictions to ESA's heliocentric projections to the Minor Planet Center's global consensus. The arc was hyperbolic, the speed was terminal, the escape was inevitable, until it wasn't. On December 31st, the shift happened. Subtle, just a few fractions of a degree, but undeniable. And at first, it wasn't the shift itself that concerned the NASA team. It was what followed. The models no longer aligned. JPL's proprietary trajectory engine, built on decades of physics, gravity harmonics, and radiation pressure modeling, started returning error margins outside of tolerance. Not failure, not collapse, but uncertainty. The object's future path could no longer be projected with confidence. This was a red flag. The default assumption was sensor error, a calibration glitch, something simple. Because natural objects don't just change course without explanation, so the data pipeline was rerun. The orbital solution was reset. Fresh inputs were layered into the simulation, from Hawaii, from Chile, from the Parker Solar Probe's latest flyby data. Still the same result, deviation confirmed. And worse, no physical explanation, no visible outgassing, no spin alteration, no coma disturbance, nothing to justify the redirection. So NASA did what it rarely does, it paused public updates. The real-time ephemeris feed, the service that projects an object's path in the sky for astronomers worldwide, was briefly suspended for recalibration. The last time this happened was during the unexpected fragmentation of comet C2019Y4, when its sudden disintegration made prediction impossible. But 3i Atlas wasn't disintegrating, it wasn't fragmenting, it was stable and still moving. The pause was subtle. Only professionals noticed it. But behind the scenes, a quiet scramble had begun. Internal emails, later obtained through independent journalists, showed that NASA analysts were debating not just the shift, but the nature of the shift. Was it a true acceleration? Was it a refractive illusion caused by unexpected surface reflectivity? Or, as one senior orbital analyst suggested, was it an instance of non-gravitational propulsion? That phrase only appears in the most extreme cometary cases. It refers to motion that deviates from the path predicted by gravitational forces alone. Usually it's caused by outgassing, sometimes by mass loss, never without cause. And yet that's exactly what this was. When the team ran trajectory reconstructions, they found that the object's heliocentric velocity had changed by a measurable, albeit small, margin. The motion had accelerated, not dramatically, not dangerously, but cleanly, like a tiny push, a nudge, something external or internal. The kicker: the new vector was more efficient. 3i Atlas wasn't tumbling, it wasn't being dragged off course. It was realigning, steering, into a new outbound arc that reduced its solar escape time by almost 3 days. That level of optimization doesn't happen by accident. One engineer described it as a gravitational ghost, because all the math works, if you invent a source of force, but if no such source exists, then the force itself becomes the mystery. And that's when the conflict started. NASA's JPL team ran the numbers again, this time expanding the modelling scope to include solar wind pressure, asymmetric radiation force, and even speculative interactions with magnetic shear zones. These fringe cases sometimes explain small anomalies in highly sensitive missions like the Parker Solar Probe or the Voyager twins, but none of the adjustments solved it. So JPL quietly updated the orbital file, changed the parameters, and released a new ephemeris. No press release, no detailed explanation, just a small change in the system, a corrected vector, a new outbound velocity. The file was labelled converged, but convergence here didn't mean understanding, it meant acceptance. Privately, sources close to the orbit modelling team admitted they were out of explanations. The internal term used was passive anomaly, a deviation that could be observed, measured and modelled but not explained. The term is used sparingly, often only for deep space probes or solar sail experiments when unexpected forces arise. This was neither of those, and still the telemetry didn't lie. The object had shifted. And the software, built on decades of orbital prediction success, could no longer tell the future with confidence. That's not just a data problem, it's a conceptual one, because when prediction fails, physics follows. No one is using the word artificial, no one wants to. But NASA's telemetry conflict left something behind far more unsettling than a trajectory shift. It left a question mark on the laws that usually hold, and right now, no one at JPL has erased it. While NASA was grappling with the silence, a shift in motion with no corresponding force, the European Space Agency was confronting light. Not ordinary light, but something sharp, brief, and impossible to ignore. ESA's Solar Orbiter, a collaborative mission launched in 2020 to study the Sun up close, had been tracking solar activity near the orbital plane of 3i Atlas for weeks. Its role was not to observe comets or interstellar visitors. It was built to study solar winds, magnetic fields, and coronal dynamics. But in the final days of December, one of its secondary imaging instruments, the heliospheric imager, recorded something strange. A narrow arc of reflected light flashed across its detection band, lasting just under 4 seconds. At first it was dismissed. A cosmic ray, a calibration glitch. Solar reflections occasionally strike sensors in unpredictable ways. But when the data was reviewed again the next morning, after the confirmed trajectory shift of 3i Atlas, the location of the flash lined up perfectly with the object's known position. That's when the European team opened to what would become known internally as the flashband file. The arc wasn't static. It moved, not across the field of view, but within a narrow range. It changed shape slightly as the object passed through a region of the solar wind with elevated density. And most importantly, it disappeared just as quickly as it appeared. There was no lingering trail, no scattering debris, no thermal signature following the reflection. The flash was clean. When the data was enhanced, another anomaly emerged. The spectrum of the reflected light did not match the known albedo profile of 3I Atlas. The object had, up to that point, shown a relatively stable reflection profile, a cool white-blue glow consistent with interstellar dust crust and carbon dioxide-rich surface composition. But this flash was brighter, sharper. It spiked across a narrow wavelength, slightly shorter than what natural eye should return, and it returned to baseline almost instantly. One analyst described it as a mirror effect. Another, less cautiously, called it a controlled glint. But what made the flashband report significant wasn't just the brightness or timing. It was the structure. The arc wasn't random, it was offset. Specifically, it was measured at roughly 420 kilometers behind the primary object body. Not forward, not along the expected tail vector, but trailing, just behind the object's motion. This led to speculation that the flash might not have come from 3I Atlas directly, but from something accompanying it, a fragment, a secondary object, a reflective plume. Each theory came with its own problems. If it was a fragment, it was behaving abnormally. It didn't drift. It didn't disperse. It stayed close, tracked with the same velocity, and vanished when the flash ended. If it was a plume, it broke every rule. Plumes don't reflect light symmetrically. They scatter. They bloom. They spread out with time and distance. This didn't. And if it was a secondary object, a piece of structure, or something tethered, then it was no longer a cometary phenomenon. It was something else. Whatever it was, it left no signature behind. No expansion trail, no particle density increase. Even the Parker Solar Probe, which passed through the outer edge of the same solar corridor, detected no particle enrichment that would be consistent with debris or mass ejection. And yet, the flash happened. It's rare for an anomaly to be this well behaved, to appear in one frame, hold coherence across a narrow angle, and then vanish without disturbing the environment around it. But this one did. That's what led the ESA imaging team to include a note in their report that would later leak to several academic circles. The note didn't speculate, it didn't accuse, it simply said, "The observed reflective event is inconsistent with cometary behavior at this proximity. Surface reflectance does not account for the angular offset. No thermal or particulate echo followed the flash. Object identity, unknown." It's the last three words that started spreading, not because they were dramatic, but because they were precise. In astrophysical terms, object identity, unknown, is not sensational, it's classification. It means we cannot, within the boundaries of current modelling, assign this phenomenon to a known natural mechanism, and that opened the door. Other observatories were contacted, the Chilean VLT, the ALMA radio array. Even small-scale optical observatories in Europe and India began reviewing images from the same time window. A handful of detections surfaced, mostly low-resolution flares that matched the timing and direction of the flashband, but none had the fidelity of the solar orbiter's original capture. The result? No consensus. Some argued it was a fragment briefly catching sunlight. Others said it was a coherent structure, a surface, a panel, a sail. One paper speculated that it was a non-bound reflective anomaly, a polite way of saying, "We saw a thing, but we don't know what the thing was." But here's what we do know. The flashband happened at the exact moment 3I Atlas changed course. The light was too clean, too narrow, too brief to be explained by dust. The reflection was offset, behind the main object, not around it. No tail structure was disturbed. No thermal spike followed. And perhaps most importantly, no one has seen anything like it before. In decades of comet observations, including close passes by Hale-Bopp, Lovejoy, and even interstellar visitor Otuose Borisov, nothing like the December 31st flashband has ever been recorded. It was sudden, it was structured, and it may have been intentional, not by a mind, not by intelligence, but by design. And if design leaves light behind, we just saw its echo. By the time dawn reached the southern rim of Earth's daylight band on December 31st, The trajectory of 3I Atlas had already crossed an invisible line, one that scientists at both NASA and ESA had been reluctant to speak of openly. Internally, they referred to it as the no-return radius, a kind of spatial marker not drawn on maps but calculated through simulations, gravitational drift projections and energy distribution plots. It was the moment when an object of this velocity, complexity and proximity could no longer continue on a harmless outbound path, and instead became entangled. Not in the gravitational sense, not yet, but in terms of observation, modelling and the weight of implications. 3I Atlas had entered Earth's forward orbital envelope, the region of solar space just ahead of our planet's motion around the Sun. It wasn't a collision path, but it was a crossing path, and that changed everything. At first, the transition was subtle. Deep space tracking stations like the Goldstone Complex in California and the Tidbinbilla station in Australia reported nothing alarming. No flare bursts, no sudden delta V changes, but the object's albedo, its reflective brightness, began to fluctuate with increasing frequency, not violently, but rhythmically, as if signalling something, a kind of optical heartbeat, and it was getting faster. NASA's infrared tracking suite at Mauna Kea logged a pulse-to-pulse interval of 38 seconds at 5 coordinated universal time. By 0610, it was down to 33. This wasn't standard light reflection, it wasn't due to rotation alone. The frequency shift suggested something adaptive, like a feedback loop reacting to solar radiation, magnetic fields, or even Earth's own emissions. That's when the atmosphere began to respond. Across the equatorial ionosphere, electron densities shifted slightly, enough to throw off the calibration protocols used in long-range GPS triangulation. Survey teams in Indonesia and Western Australia reported minor drift errors. No one connected them to Atlas at first. These were dismissed as local disturbances, possibly solar wind effects or radio interference. But then came the distortion corridor. At precisely 0732, 3 weather satellites, Suomi NPP, Fengyun 3C, and NOAA 20, all captured something unexpected from different orbits. It wasn't an image, but a lensing. A small strip of atmosphere, just above the South Pacific Convergence Zone, appeared slightly warped. Not visibly, but thermally. The air there refracted outgoing long-wave radiation in a way not previously observed. It bent heat, not like a mirage, more like an inversion. By the time the data reached interpretation teams in Boulder and Toulouse, 3I Atlas had already passed the midpoint of its crossing path, and from that moment forward, the entire behaviour of the object began to shift, the tail alignment inverted. Not gradually, but with sudden purpose. For weeks, Atlas had held a consistent tail configuration, the primary tail flowing away from solar wind vectors, the secondary anti-tail leaning toward its point of origin. But now both structures bent inward, forming a wide V-shape that pointed toward Earth's orbital plane. The tail was no longer just expelling, it was steering, and that meant only one thing: the comet, if it could still be called that, was actively adjusting to a new frame of reference. Not just the Sun, but Earth. For planetary defense analysts, this was the point of no return, not because Earth was in danger of impact, but because it was no longer possible to claim ignorance. This object wasn't passive. It wasn't on a decaying hyperbolic trajectory through our system. It was observing, it was recalibrating, and most disturbingly, it was synchronizing. Dr. Alondra Baines at the Jet Propulsion Laboratory put it plainly during a private call with ESA counterparts. We have to stop modelling this as a comet. It's something else, something with adaptive feedback. This isn't a rock or an ice body, this is responsive behaviour. The implications of that one sentence sent ripples through internal communication chains, because responsive implied agency, not life, not intelligence in the biological sense, but system-level reactivity. Like a machine interpreting new data and shifting its outputs. As 3I Atlas crossed into the outbound limb of its intersecting arc, the final observational proof emerged. A low-frequency radio echo bounced off its forward shell, if it could still be called that. The signal came from a test ping fired from the ESA's Gaia probe, never meant for public release. But the echo returned, not as noise, but as a harmonic. The signal that bounced back was cleaner than expected, with a doubling resonance pattern that suggested some kind of internal structure. This wasn't just rock. This was reflective, geometric, possibly layered. And that echo confirmed what some had feared since the beginning. 3i Atlas was no longer a wandering anomaly. It had noticed us. It had entered our orbital corridor. And whatever it was doing, it wasn't finished. The point of no return was never meant to be dramatic. It was a quiet, analytical boundary in the minds of those tracking it. But now, as December 31st moved steadily toward noon, and the object's pulse continued to increase, that once theoretical line had been crossed, and there was no going back. It wasn't just the visible shift that caught scientists off guard. As soon as 3i Atlas pivoted in its trajectory, something even stranger unfolded. The thermal signature dropped, not faded, dropped, almost like a curtain had been pulled over the infrared sensors aimed at the object. In the moments leading up to the turn, NASA's infrared arrays, specifically those tied to high-orbit telescopes and the James Webb's thermal baselines, had been tracking Atlas with consistent temperature data. It wasn't spectacular. Just the usual heat signature of a comet-like object bleeding off solar warmth after perihelion. But the moment it pivoted, the temperature profile dipped below instrument thresholds. Not partially, fully. Teams initially assumed an instrumentation fault. They checked for solar interference, cosmic rays, thermal lag, every known variable that could skew a reading, but one by one they ruled them out. The problem wasn't with the sensors, it was with the object itself. It had stopped radiating heat, or more precisely, it had stopped radiating heat in any way human instruments were capable of detecting. This wasn't just an academic issue. Infrared suppression on this level had only been documented in two contexts: deliberate thermal shielding in stealth aerospace engineering, or deeply anomalous celestial bodies with unknown structural properties. But Atlas had just made a sharp gravitational maneuver, something comets don't do. Now it was cloaking its thermal emissions. That wasn't just unprecedented. It was provocative. What deepened the mystery was the consistency of the suppression. Even after triangulating from multiple sensor angles, using infrared arrays in Chile, Arizona, and high Earth orbit, no thermal readings emerged. A once warm object, now radiating nothing. The silence wasn't just sensory, it was psychological. NASA had never dealt with this kind of emptiness before. The terminology changed again. Internally, some reports stopped calling Atlas a comet. Instead, it was labelled an unresolved thermal vector, not because it made scientific sense, but because there were no better words. Something had turned, something had gone cold, and not metaphorically, literally cold. What truly unnerved mission control was the realization that if Atlas had the capacity to control its own heat emissions, then it was actively managing its visibility. It was deciding how to be seen or not seen. That wasn't comet behavior, that was calculus, and the math was being done by something else. While NASA scrambled to understand the thermal silence, another agency picked up something just as strange, but in a completely different spectrum. The European Space Agency's swarm satellites, designed to monitor fluctuations in Earth's magnetosphere, began registering localized distortions that matched the window of Atlas's sudden directional shift. It started faint, just a blip in the scalar gradient where the ionospheric layers thin near the poles. But then the pattern intensified. The wake left behind by Atlas's turn was not just optical or thermal, it was magnetic. A ripple of magnetotail interaction began extending outward, not toward the Sun or the Earth, but laterally, like a sideways wave of compressed field lines. Normally, comet interactions with solar wind produce turbulence, disturbances, tail flickers. But this wasn't turbulence, this was order, a harmonized, banded pulse that moved as if it had choreography. When converted into audio frequency maps, a common diagnostic technique in space physics, it generated tones, structured tones, like a call and response signal bouncing between field layers. ESA scientists, initially skeptical, now began to collaborate with counterparts at JAXA and NASA. The signal's repeat pattern didn't match any known interference. It wasn't echo. It wasn't reflection. It was something closer to modulation, a pattern that seemed to anticipate field resistance and move around it. This had two profound implications. First, Atlas wasn't just interacting with magnetic fields, it was influencing them, And second, its motion through space wasn't passive. The object seemed to know where the magnetic seams were, like it was tracing a path of least resistance through an invisible map only it could read. The term that surfaced across analyst briefings was intelligent navigation. Not in the science fiction sense. There was no claim of life, no declaration of extraterrestrial design. But what they were seeing followed rules that didn't align with natural debris. There was intentionality in how Atlas moved, and now in how it left trails behind. By late afternoon, the ESA's modelers introduced a new possibility. What if Atlas wasn't just turning for observational purposes? What if the maneuver was about field alignment, a kind of calibration using Earth's and Jupiter's overlapping magnetospheres as markers? That idea alone rewrote everything, because it meant Atlas wasn't just moving, it was steering, not randomly, but with orientation, with relationship, with response. And the magnetic wake it left behind wasn't just residue, it was part of its motion signature. And here's what made it all worse. The wake was slowly approaching Earth's own magnetopause, not directly, but adjacent, like a veil brushing against the outermost edge of our planet's magnetic shield. That proximity raised a final, chilling question. If the object was responding to magnetism, and Earth was now within reach, what would happen next? The turning of 3i Atlas wasn't just a disruption in its path, it was a disruption in our models. What we witnessed in the hours following its directional shift on the morning of December 31st was something that didn't quite fit into any existing framework. For the first time, the orbital projection tools at NASA's Jet Propulsion Laboratory began spitting out results that contradicted themselves. This wasn't a failure of the data, it was a failure of geometry. The path of the object no longer adhered to the expected parabolic curve we had assigned. That curve, based on gravitational interaction, solar influence and trajectory history, had been stable for months. But now, as new observations poured in, the system struggled. Instead of a neat arc or spiral, Atlas began exhibiting what mission analysts called pseudo-orbital artifacts. In plainer terms, it wasn't turning according to any known rule of planetary motion. Some called it a computational anomaly. Others said it was an interpretive illusion, brought on by a tail-wide distortion field. But when visual data was overlaid on magnetometric scans, a pattern emerged, and it was one we hadn't anticipated. The object wasn't drifting, it was folding. Or more precisely, it was moving along a path that curved through more than just three-dimensional space. The analogy that gained the most traction within the astrophysics community was this. Imagine watching a bird fly across the surface of a lake, but realizing later it was moving through the water just beneath the surface all along. What we were seeing wasn't just misleading, it was incomplete. That failure of geometry, the way 3i Atlas bypassed our mathematical lenses, created a silent rupture in the field. For the first time in decades, veteran orbital physicists began pulling out speculative papers from the back shelves of academia. Old theories, once discarded for being too speculative, suddenly felt like they might be the only maps we had left. Because if 3i Atlas could turn on a vector that didn't belong to its own mass, if it could fold light and path in a way that confused our best instruments, then what else had we misunderstood? And more importantly, what else was about to fail? Most objects that veer this close to the Sun, especially those made of volatile ices or dust-laden carbon matrices, don't leave unscathed. They fragment, flare out, or simply disintegrate under the pressure of solar radiation and gravity. But not 3i Atlas. When it passed the solar threshold, something else happened. It retained form. Not only did it survive the perihelion, that blistering closest approach, but it seemed to emerge stronger. Multiple observatories noted a phenomenon that was first dismissed as noise, an increase in tail density not after the solar pass but during. That's not how comets behave. That's not how matter reacts to fusion-level radiation. Instead of being stripped, the object appeared to thicken. Its primary jet doubled in brightness, while the reverse tail, the one facing away from the Sun, shortened as if something internal was adjusting the flow, and that adjustment wasn't random. Spectral analysis revealed a shift in emission bands. Where before there had been signs of carbon and trace metals, the classic fingerprint of a comet, Now there were harmonics consistent with compounds we hadn't catalogued. One researcher described it as light being filtered through something reactive but stable. Another simply called it unnatural resonance. The core, once presumed to be a loose agglomeration of debris, began to pulse faintly. That pulse wasn't visual, not to the naked eye. It was radiative, a wavelength just shy of deep infrared, but it repeated every 68 seconds without variation. So what had the sun failed to destroy? Possibly a structure. That idea sent quiet ripples through the scientific community. A comet that doesn't burn is not a comet, and yet calling it a spacecraft was too bold, too speculative, too dangerous. So they settled, publicly, on anomalous body. Internally, however, the conversation had already shifted. What material could endure that level of heat without charring, melting, or fragmenting? Why did the emissions become more complex after solar exposure? And what was that internal signal doing? Broadcasting, scanning, or regulating? One thing was certain. We had just watched 3i Atlas pass a test. Not one we gave it, but one it may have been built to endure. And if that were the case, then its path through our solar system might not be a passive flyby at all. It might be part of a sequence, a protocol, a mission. And if the sun was the crucible, then 3i Atlas had just proven itself unburnable. As dawn broke over Hawaii, a new reading emerged from the Mauna Loa Solar Observatory, one that immediately caught the attention of NASA's Deep Space Telemetry team. For a brief period, just under 7 minutes, the local magnetometer registered a layered field distortion. It wasn't strong, but it was distinct, and it wasn't terrestrial. It was as though something had brushed past Earth's electromagnetic boundary, but no satellite had crossed the detection zone, no solar flare was incoming, and no CME had been reported. What remained was a residual anomaly, an oscillating wave pattern unlike any recorded from natural sources in that sector of space. The signal was clean, rhythmic, structured. At first, the team suspected interference from one of the Starlink satellites. Those occasionally triggered similar misreadings. But after triangulating with data from the European Space Agency's Lagrange point monitors, the same ripple was confirmed. This wasn't a local distortion. It was something in the interplanetary medium, something moving with precision, as if tracing a boundary between gravitational gradients. And at its epicenter was 3i Atlas. Not in terms of location, because the object had already moved further along its arc, but in terms of influence. Every layer of sensor data pointed to a central origin, and when plotted, the pattern of the disturbance mirrored the curvature of Atlas's previous tail alignment. A shape had been left behind in the field, not static, not glowing, but present, embedded. Scientists debated terminology. Some wanted to call it an echo field. Others suggested a form of field memory, an idea not typically entertained outside of theoretical physics. The concept was simple, that a sufficiently charged body, if spinning or emitting in the right geometry, could temporarily imprint a signature on the local space-time fabric. It wasn't proof of intelligence, but it wasn't random either. What concerned researchers most was what happened next. The field did not disperse as expected. Instead, it held, faint but measurable, and over the next 2 hours it began to rotate, not on its own axis but in response to solar alignment. It was aligning again, not to Earth this time, but to something further. One of the models showed it pointing, briefly, to a region near Neptune's orbital plane, but that wasn't where Atlas was headed. That wasn't where anything visible was. And yet, the rotation continued. Not wild, not drifting, calculated. It was as if the residue itself was being pulled, not by gravity but by instruction. This was the moment when theories stopped being academic. Because for the first time, space itself was showing signs not just of reaction, but of retention, a memory of motion, a follow-through of force, the kind of thing that, if observed in a lab, would raise questions of programming. But this wasn't a lab. This was the vacuum of space, and something out there had just drawn a circle in the invisible. Even before the field distortion had fully rotated, radio astronomers in New Mexico noticed a change, not in what was coming through, but in what was missing. For months, Atlas had emitted a low-level pulse in the background, inaudible to the human ear, but consistent enough to form a predictable hum in the deep space radio frequencies. Most comets don't emit in radio, but 3I Atlas had, and until now it had been steady. On the morning of December 31st, that signal went silent. Not abruptly, not like a power down, more like a fade. The frequency narrowed, the amplitude softened, and then, within 6 minutes, it flatlined. Instruments showed no hardware failure. Solar conditions were normal, and every other known background emitter remained stable. Just Atlas, gone quiet. The silence triggered a rapid protocol across multiple agencies. Within the hour, observational tasks were reprioritized. Antenna arrays in Australia, Greenland and Chile were retasked. Even the Chinese Deep Space Network adjusted one of its high-gain dishes to reacquire the source. Nothing, not a blip. But what they did see was something stranger. Instead of silence, a kind of harmonic displacement had started to show, an interference pattern not unlike the ones seen near black holes, but without the gravitational lensing. It was as if the space surrounding the last known trajectory of Atlas had become thick, slower to propagate signal, not blocked, just bent. And then, without warning, a single tone returned. Just one. It was narrow, perfectly symmetrical and completely artificial in structure, a frequency not found in nature. At first, it seemed like a glitch, but 3 separate stations picked it up, and it held for precisely 9 seconds. Then it stopped. The scientific term would be a burst, but this one didn't fit the standard model. It had no tail, no build-up, just on and then off. But within that signal was embedded something even more unnerving. A ratio, not a message, not language. A simple numerical proportion that matched the golden angle, used in biological spirals, galaxy formation, even neural mapping. And that's when the conversations changed tone. Because if Atlas wasn't just broadcasting, but measuring, then the silence wasn't absence. It was data, compressed, structured, and now, maybe, handed off. To what, or whom, no one could say. But the silence had ended, and what came in its place was not noise, it was precision, and precision doesn't happen by accident. When the imaging teams at Mauna Kea Observatory began reviewing a sequence of near-infrared observations from the night of December 30th, they were looking for confirmation of a subtle curve change in 3I Atlas's trajectory. But what they found instead brought them to a complete stop. The data revealed a secondary reflection, weak but consistent, that hadn't been present before. And more intriguingly, it wasn't coming from the comet's known tail structure, nor from solar bounce. It was originating from space itself, specifically from a position trailing just behind Earth's magnetotail. The initial thought was simple: background noise, cosmic interference, a glitch in alignment. But each frame reinforced the same phenomenon. The secondary glow didn't shift like a background star. It moved with the Earth. More precisely, it responded to Earth's magnetic signature. This type of synchronized light behavior hadn't been recorded before. It wasn't a flare. It wasn't a ghost image. It appeared to be a faint echo, a reflective ripple, mirroring the turn that 3I Atlas had made earlier that morning. It was like seeing a comet's decision echoed in the space behind us. For weeks, analysts had debated whether the object's real-time decisions, its jet shifts, its plasma irregularities, its non-random accelerations, could be linked to Earth's magnetic structure. But until this moment, nothing had visually tied it to us in such a literal way. Now there was a pattern emerging that defied gravitational logic. When Earth passes through regions of high solar wind, its magnetosphere flexes and contracts. That's basic space weather. But what was being observed here wasn't the result of compression or particle flux. It was something altogether different. A glow that mimicked the arc of 3I Atlas's turn, except this time from the opposite side of the solar system's map. It was as if our planet had become a lens, or a relay. This ignited a new line of inquiry. Could 3I Atlas be projecting something back through the very medium we observe it through? Could it be bouncing information, directional data, perhaps off of Earth's magnetic field? To test this, the observatory correlated timestamps from the flare-like mirror to a known burst of directional plasma emitted by the object just hours earlier. The timing aligned to within 7 seconds, and in those 7 seconds, Earth had rotated precisely enough to face its magneto-tail away from the Sun, toward the object's new vector. That's when a hypothesis was quietly introduced into the ESA's discussion thread. 3 Atlas was not merely reacting to gravity or solar wind, it might be reacting to us, or more specifically, to how we interact with space itself. Whether this was an unintended effect, a byproduct of its trajectory, or something far more intentional, was impossible to say. But one thing was clear. For the first time, Earth had cast a shadow that reflected more than just light. This wasn't a tail flare, it was a message flicker, and perhaps a response. As solar telescopes across the Northern Hemisphere adjusted to track 3I Atlas through its reoriented path, they stumbled on a new form of irregularity, not in the tail, not in the plasma waves, but in the delay. For nearly 3 minutes, during a quiet window around 0642 Universal Time, ground-based receivers began picking up signal drift, the kind you would expect when a massive geomagnetic storm disrupts satellite communication. But this wasn't caused by any storm, and there were no solar flares to blame. What changed was the timing of signal return between Earth-based relay satellites and deep space beacons. The pulses bounced between them showed latency that pulsed at exact 20-second intervals. Too short for solar weather interference. Too long for hardware hiccups. What emerged was a wave, rising and falling like a heartbeat, across multiple devices that weren't connected through shared infrastructure. It was NASA's Deep Space Network that caught the anomaly in 3 locations simultaneously: Goldstone in California, Madrid in Spain, and Canberra in Australia. All 3 detected the same rhythmic delay, and at the same moment, a narrowband transmission burst was recorded, subaudible, sub-radio wave, on a frequency that had previously only been modelled in lab-grade simulations of theoretical field harmonics. The signal was faint, just 4 pulses, then silence. But when decoded into waveforms, something eerie appeared. Each pulse was shaped identically. Not in frequency, but in structure. The peaks and troughs aligned with near-perfect mathematical symmetry. Not random. Not ambient, deliberate. What startled researchers wasn't the presence of the signal, it was where it originated from. The triangulated origin was not 3I Atlas directly, nor from the Sun. It came from a corridor, an invisible region, that connected Earth to the new path of 3I Atlas's tail. In orbital modelling, this path was previously known as a blind vector, a gap between known orbital positions. It had never held significance, until now. This pathway, what astronomers now dubbed the Earth line, acted like a transmission tube, not visible, not traceable, but spatially resonant, like a stretched string vibrating between 2 tuning forks. If 3I Atlas was broadcasting, it wasn't broadcasting to all. It was using a spatially narrow, time-sensitive channel that passed directly through Earth's magnetic field. What that meant, no one could fully say. But there were theories. Some posited that the object had recognized Earth's field as a mirror, a way to bounce signals back into the solar system without expending energy. Others suggested something more speculative, that Earth's position wasn't incidental, that we were being used as a node, a filter, a resonant point. The implications were staggering. If true, it meant that 3I Atlas wasn't just observing Earth or moving through gravitational paths, it was utilizing the very structure of our planet as part of a larger network, a data relay, or worse, a translator. But amidst all the theories, one conclusion rose to the surface like a cold truth. This was no longer a passive object being tracked through the solar system. This was interaction. This was alignment. This was 3I Atlas stepping beyond movement and into intention. And in the silence that followed the final pulse, the only thing left was the Earth itself, still spinning, still receiving, still waiting. The phenomenon wasn't supposed to be visible, and yet it was. As 3I Atlas settled into a more consistent trajectory, a strange secondary effect began to appear in the data, specifically in the emissions trailing from its ion tail. Analysts first noticed it when comparing long-exposure composite images from ground-based telescopes in Chile and South Africa. A faint duplication effect, barely perceptible, began manifesting along the edges of the tail, At first it seemed like a lensing distortion, but the pattern didn't shift with atmosphere. It followed the object. This subtle double image, this ghosting along the edges, wasn't an illusion. It was real. Instruments tuned to ultraviolet spectrums confirmed that the mirrored silhouette was composed of the same charged particles emitted by the main ion stream. But these secondary emissions were not aligned to the primary solar wind direction. They curved differently. They reflected, not emitted. That's when the language began to change in the labs. The term reflection had been reserved for photonic effects, for surfaces and atmospheres and glints. But here, in the tail of a deep space object, something was bouncing. Not light, but structure. The ion stream had started to behave like a reactive mirror. This was unprecedented. Comets don't reflect behaviourally. Their emissions are reactive, sure, driven by solar radiation, charged winds, gravitational shear, but they don't encode patterns, and they certainly don't mimic themselves in real time across dual trajectories. Yet the mirrored tail held firm across multiple viewing windows. It pulsed with the same rhythm, just inverted. Phase-locked, but reversed. Avi Loeb, the Harvard astrophysicist known for his work on interstellar visitors, remarked in a press call that this kind of mirroring effect was not something predicted by any comet interaction model. Not with solar plasma, not with magnetic fields, not even with hypothetical ion traps. If the tail was acting like a mirror, then something was causing it to bounce energy, or information, back into itself. That meant some form of feedback, and feedback in systems theory implies one of two things: instability or control. Further complicating matters was the location of the mirror anomaly. It didn't begin near the core of 3I Atlas as one would expect. It emerged halfway down the tail, precisely at a region where emissions should be dissipating, not cohering. And yet, the density data suggested something else entirely. The mirrored emissions were strengthening. They weren't fragments, they were forming structure. And then came the stunner. A thin band of electromagnetic interference, previously chalked up to background noise, was reanalyzed through a separate data channel. It showed a signature modulation frequency, one that mirrored the timing of Earth's Van Allen radiation belt pulses. This wasn't just mirroring, it was echoing. NASA, for the first time in this mission, issued a quiet internal memo to all observatories coordinating on the 3I Atlas project. The phrase was tucked near the end. Unexpected tail harmonics detected. Comparison to Earth-based magnetic patterns ongoing. Please submit high-res datasets on delay drift and waveform matching. It was a formal acknowledgement that something was being recognized. Not just observed, recognized. And if recognition was involved, then the implications extended far beyond mere cometary behavior, because what mirrors can see. Inside the isolated vacuum chambers of CERN's data modeling labs, something had started to drift. Not physically, temporally. Instruments designed to monitor particle decay and electromagnetic coherence began showing a slow but measurable shift. Initially attributed to routine calibration lags, the shifts gained attention only after 3 separate labs, each on different continents, reported the same anomaly within a 6-hour window. Particle clocks, which typically maintain a near-perfect rhythm when tuned to external cosmic ray sources, had begun to wobble. At first glance, it was barely worth mentioning, a fraction of a second across thousands of cycles. But that fraction wasn't random, it was rhythmic, predictable, and it matched a waveform pattern last seen in the ion tail of 3I Atlas. That connection was supposed to be impossible. Particle clocks don't take signals from comet tails millions of kilometers away, but when the waveform overlay was completed, comparing the decay drift curve with the harmonic pulses in the tail, the fit was undeniable. It was as if something had injected a metronome into the field itself. A soft tick, a quiet hum that synchronized not just emissions, but temporal rhythm across distinct systems. The implications were staggering. If 3I Atlas was emitting a field that could influence localized systems on Earth, not just magnetically, but temporally, then it wasn't merely passing through space, it was resonating through it. This idea triggered a flurry of responses in the astrophysics community. Theoretical physicists suggested that a kind of temporal scaffolding might be emerging, a phenomenon where high-energy emissions interact with dark matter pockets, briefly creating a harmonic structure in the flow of time itself. It sounded absurd, and yet, The data held. One experiment tucked away in a research paper from a small Japanese observatory showed that light pulses directed through a polarized gas chamber experienced microsecond distortions. Distortions that corresponded to the same intervals seen in 3i Atlas's tail pulses. The photons weren't delayed randomly, they were being bent by a rhythm. NASA issued a public-facing clarification, calling these findings early-stage observational anomalies requiring further verification. But internally, the word temporal influence began showing up in more documents, quietly, carefully. Then came the real twist. On December 31, deep space observatories tracking the plasma field around 3i Atlas reported something never before seen in a comet. A pulse burst that was entirely silent in traditional energy bands. No gamma, no infrared, no X-ray. And yet, timekeeping stations on Earth detected a synchronous blip. An unexplained compression event lasting less than a millisecond. Short enough to dismiss. But the fact that it occurred globally, across every atomic clock system, was undeniable. This was no longer a comet. Not in the classical sense. It was a regulator, a clockmaker, a signal embedded in orbit. And the deeper question began to rise, not just in the labs, but in the minds of those watching. What was this object timing? And who? Or what? Was it timing it for? In every recorded study of celestial dynamics, one principle has remained consistent. Mass follows a predictable path. Whether governed by Newtonian laws or relativistic tweaks, the motion of an object through space should obey the gravitational contours laid out for it. But what unfolded on the morning of December 31st defied even the most forgiving simulations. After 3i Atlas executed its unexpected axial turn, its projected path veered off, not by a minor correction, but by an entirely new arc. An arc that no celestial body of this size, shape, or mass should be able to follow. Initially, the change was assumed to be observational error, perhaps a minor miscalculation in Doppler shift, or interference from the solar wind. But after several terrestrial observatories in Chile, South Africa, and northern Australia confirmed the exact same anomaly using independent equipment, the error was ruled out. This wasn't noise, it was motion, controlled motion. The deviation in trajectory suggested not just a passive drift or gravitational slingshot, but a powered vector correction, as if 3i Atlas had responded to something. The curvature wasn't a soft bend. It was an angled redirection, sharp yet continuous, like the turn of a rudder in fluid. Except this wasn't fluid. This was the vacuum of space, with nothing but cold gravitational wells scattered far between. NASA's orbital mechanics team, usually known for their composure, issued an internal alert level upgrade. Not for risk, but for sheer statistical improbability. They calculated that the new arc required a sustained alteration of momentum, not feasible with any known outgassing force. The change in path was simply too stable, too clean, and, most telling of all, too efficient. More curious than the path itself was where it now pointed. The object was no longer approaching Jupiter. It was now rising along a curve that would lead it, if the vector held, toward a region of space historically considered observational dead zone. A quadrant sparsely populated with known objects, radio quiet and magnetically benign. In the language of the celestial cartographers, it was nothing, a void. But to 3i Atlas, it suddenly seemed important. A quick review of that region's past telemetry revealed something else. A faint spike had been recorded in that direction exactly 31 days prior. A brief, non-repeating signal that was logged and dismissed. Too weak, too vague. But now, in retrospect, it looked like a beacon. A signal, perhaps. And 3i Atlas was headed straight for it. The object wasn't just turning, it was answering. And with every kilometre it travelled along this impossible trajectory, one truth began sinking in deeper across the scientific community. 3i Atlas wasn't reacting to our gravity or our models, it was following a purpose we had not yet mapped. For decades, scientists have known how space reacts to mass. Large bodies bend the space around them, creating the orbits and dynamics we call gravity. But what unfolded around 3i Atlas in the hours after its directional shift wasn't just gravity, it was distortion, a bubble of refracted space-time that seemed to stretch not only light, but signal itself. The earliest clue came from a deep space array in northern Scandinavia. researchers noticed an unusual signal lag, not in the data rate itself, but in the time it took for pings to echo back from a cluster of passive satellites. A delay of fractions, then full seconds. When recalibrated through redundancy paths, the lag disappeared, but only when the signal rerouted away from the visual corridor of 3i Atlas. In short, anything sent through that zone bent. Infrared scans revealed even more disturbing data. Stars behind the object appeared subtly smeared, not by lensing, but by what analysts described as a gravitational haze. Not a hole, not a warp, a shifting envelope, like heat rising off the pavement, but with geometry instead of temperature. This distortion field didn't behave like any known cometary coma. It wasn't composed of ionized gases or solar reflective dust. In fact, it didn't register as particulate at all. Instead, it showed a frequency spread, an energetic signature so fine it almost resembled quantum interference. Whatever surrounded 3i Atlas wasn't just deflecting matter, it was blurring the boundary between position and observation. Physicists at Caltech proposed a staggering hypothesis, that 3i Atlas was cloaked in a modulated field designed to buffer external forces. The idea wasn't to hide, it wasn't stealth, it was insulation, a cocoon, not from detection, but from influence, as if the object required a stable internal environment, free from even the soft chaos of electromagnetic variance. This would explain its perfect trajectory shift, its resistance to spin drift, its ability to hold structure during solar exposure without venting or breaking. Most comets fracture under solar radiation. Most meteoroids spin unevenly or break apart from torque. But 3i Atlas moved like something protected, not merely dense, but shielded from the rules of normal physics. Further supporting this idea was the lack of secondary debris. Usually when an object of this mass enters a turn or begins to vent energy, it leaves a trail, outgassed particles, pebble-sized fragments. But behind 3i Atlas, nothing lingered. No haze, no wake, only light bending and silence. The ESA's Gaia Observatory was the first to suggest a possible framework, localized spacetime modulation, a concept long theorized but never observed. It involves the controlled thickening or thinning of the very fabric around an object to reduce inertial friction. Not propulsion, adaptation. If true, it would mean that 3i Atlas was doing something no natural object had ever done. It wasn't moving through space, it was adjusting the medium around itself, thinning the river to let it glide or thickening the banks to stay still. Whatever it was doing, it had clearly entered a new phase, one where its behaviour was no longer explainable by cometary physics, but by something else entirely, something that began with structure and now ended with intention. By the time morning light spilled over the Pacific observatories on December 31st, the final readings of the night before had already begun reshaping quiet conversations across deep space agencies. It wasn't a collision, it wasn't an explosion, there was no singular moment of impact. Instead, what marked the turning point was subtler, more elusive, a shift, a directional realignment of 3i Atlas so minute in visual terms that it could have been mistaken for calibration noise. But it wasn't noise, it was a vector correction. Somehow the object had issued a smooth change in its own heading without external force. No gravity assist, no visible plume, no outgassing behaviour that could account for even a fraction of the manoeuvre. And yet the math was solid. Over the course of a 6-hour observation window, the object's path deviated by a fraction of a degree. Barely perceptible to the naked eye, but at this scale that was vast. Over days, it would place 3 Atlas in a new corridor of space, one that didn't exist on any of its prior orbital projections. The implications went beyond astronomy. This wasn't about trajectories anymore, it was about decisions. A shift in course implies awareness, or, at the very least, input. And if there was input, there was some form of control, not random, not reactionary, controlled. That word, controlled, began appearing in the closed-door briefings, not theorized, not speculated, quietly noted in slides, embedded as a term of necessity. The standard models could no longer contain what was happening. The behaviour of 3i Atlas had moved beyond the language of rock and ice. It was becoming a system. A logic, a sequence, and that's when the secondary metrics began to change. High-frequency magnetometer readings, the kind used to monitor spacecraft shielding efficiency, showed subtle undulations, as if 3i Atlas was emitting pulses not in the visual band but in magnetic form. A heartbeat, if you will, not a mechanical one, but a recurring pattern that behaved like a signal tracer. It echoed faintly in the upper ionosphere. It wasn't loud, it wasn't harmful, but it was synchronized. Once every 47 minutes the readings peaked, first in low Earth orbit, then hours later across lunar relay stations. The signal was directional, it was tracking Earth, then bouncing off the Moon. This shouldn't be possible. Comets do not emit coherent frequency pulses. They do not adjust their trajectory by fractional degrees to enter solar corridors they've never occupied before, and they certainly don't sync their signal windows with the orbital position of Earth's natural satellite. But here we are. By midday, the word had spread from tracking teams to astrophysics liaisons, and from there into emergency advisory boards for planetary motion protocol. No one said the word threat, but no one said natural behaviour either. Instead, they used a phrase that hadn't appeared in this context before: structured autonomy. It was a placeholder, a way to describe what couldn't yet be categorized, the sense that 3i Atlas wasn't just surviving the solar environment, but interacting with it, observing, reacting, possibly even adapting. And in that recognition came a deeper, more unsettling truth. Perhaps the turning of 3i Atlas wasn't the anomaly. Perhaps the anomaly was us, witnessing for the first time a level of intention embedded within a body we had spent months calling a comet, a fragment, a remnant. But now, as the signal repeats and the heading shifts, we begin to understand. This object may not be here to collide, to destroy, or even to contact. It may be here simply to cross a threshold, a boundary we didn't know existed until we saw it move. As the final image stack was transmitted from the farthest sensor array orbiting beyond Mars, a kind of stillness settled across the global observatory network. Not because the signals had stopped, not because the object had vanished, but because for the first time humanity saw something shift in space, and we had no equation to explain it. The world didn't pause. The skies didn't open. Satellites continued their cycles and power grids hummed steadily beneath the surface of our routines. But in the quiet corners of the astrophysics community, something had changed. It was a change not in facts, but in framing. For months we had viewed 3i Atlas through the lens of motion and matter, trajectory, composition, albedo, acceleration. We called it interstellar. We called it volatile. We labelled its tail. We modelled its coma. We stacked every piece of data through algorithms trained to extract predictability from chaos. But now, none of that seemed sufficient. A simple, silent turn, not accompanied by thermal discharge, not caused by planetary proximity, and not following gravitational expectations, has shifted our understanding from the what to the why. It's no longer just about observing a foreign object. It's about accepting that it might be observing us back, not as a conscious entity in the way we define consciousness, but as something structured, something not behaving randomly, something acting within a system we have not yet mapped. And maybe that's the part that unnerves us the most, because space is supposed to be silent, cold, predictable in its violence. But 3 Atlas is not behaving violently, it's behaving methodically, as if it is not simply travelling, but responding. As if this turn, imperceptible to the naked eye, is not just motion, it is instruction. For those watching closely, the tension doesn't come from spectacle. It comes from restraint, the kind of intelligence that doesn't need to flash or flare. It doesn't announce itself. It just shifts, slightly, as if to say, I see you. And in that quiet message, if it is a message, we are forced to confront something we haven't faced since Voyager first left the solar system. The question of presence, not invasion, not contact, just presence. What does it mean to detect not just mass, but intention? What if this object was never a threat, never an emissary, but simply a signal, a moving structure encoded with behaviour designed not to interact but to be noticed? Like a lighthouse beam in the black sea of interstellar space, meant only to turn at the right moment. And if so, what are we now that we've seen it? Because with that turn, we are no longer observers. We are part of the equation. Our instruments responded, our trajectory models updated, our agencies convened. 3i Atlas didn't just change course. It changed our role, from passive watchers to quiet witnesses of something larger, and maybe that's the story. Not the anomaly, not the panic, but the quiet shift in our assumptions, the ripple in our models, the slow, irreversible realization that space still holds structures we cannot classify, and that some of those structures may hold their own timing, their own logic, and maybe even their own awareness. For now, we wait. Not for contact, not for catastrophe, but for whatever comes after the turn.